So welcome, Yulij Sergeevich. It's a pleasure to receive you again.
Buenos dias to everybody. The lecture today is quasi-conformal mappings as a way to simultaneous uniformization. It is a very long word, quasi-conformal, and in future I will abbreviate it like this. As a way to simultaneous uniformization. Once again, simultaneous uniformization will be many times on the blackboard. And I will abbreviate it as SU. The goal is to uniformize a family of algebraic curve with which is the family is topologically trivial. So we have algebraic curves, Riemann surfaces, compact Riemann surfaces with a finite number of punctures that in a sense depend analytically on the parameter. You have a family of algebraic curves like this. And you want to uniformize them simultaneously. That is, you take a universal cover over each of these surfaces, you map it to a topological disk biholomorphically, and you want that this biholomorphic map will be not only holomorphic on the universal cover, but depend analytically, holomorphically, on the parameter of the family. I will give you a precise statement a little bit later. I recall you what algebraic curves are. This is zero sets I define algebraic curves in a particular case, so-called affine algebraic curves in C-square. They are zeros of polynomials of two variables. If the degree of a polynomial is n, then in generic case, this is S, S is generically. That is, for almost all values of the coefficients of the polynomial Pn. Generically, S is a compact surface of genus G with n punctures. This is a sort of a picture like this. A compact surface with endpoints deleted. And even Riemann, who introduced Riemann surfaces, discovered the formula for G. It is called Riemann-Hurwitz formula. So this is the situation which will appear many times during the lecture today. I recall you that there are so-called deck transformations of the universal cover. Let me denote it as hat. Sometimes the notation will be changed to phi, but right now I keep it S. So we take the Riemann surface, we take the universal cover of classes of paths that are homotopic on S. You take a 0 point, a base point B0 on surface S, and you have a simply connected surface S hat with the base point B0, any curve on S, even a closed one, is a simple arc, and this is the point gamma hat. And in fact, any curve homotopic to gamma represents the same curve on the universal cover by definition. And there is a map G gamma of the universal cover onto itself. Any curve, say lambda, comes to lambda, and first gamma is Ren. So any curve lambda comes to a curve gamma. And for this, we have for the universal cover, you get a so-called deck transformation. Gamma hat comes to gamma lambda hat. Now, a great consequence of the uniformization theorem comes. In case when the genus G is greater than 1, it will be our case all the way, you have, by the uniformization theorem, a conformal map of the universal cover to the upper half plane. This is the upper half plane, this is the lower half plane. I stated the uniformization theorem as existence of the conformal map to the unit disk. But on the Riemann sphere, it is the same as to take the unit disk or the upper half plane. You can just map the unit disk to the upper half plane by the Möbius transformation. So we will keep this form of the uniformization theorem. This is the map J gamma of the universal cover to itself. And if you take a point here, then you can define the map, the image of the point here, under the deck transformation. You should take the inverse image of this point here, then its image under the deck transformation here, and then the image of this point under the uniformization map. And this will be G gamma. And G gamma is h to the negative 1, J gamma, h. And this is a conformal map of U to U. And in the general of complex variables, you are told that such maps are transformation. So, any compact Riemann surface generates a group of Möbius transformations the set of G gamma, for which gamma are elements of the fundamental group of S, is a group G of Möbius transformations. And this group is discrete. G is, in a sense, discontinuous on U. No orbit of G is just a result of applications of all elements of G to a point in U. So this is orbit of this point under G. No orbit of G has limit points in U. Only on R. Such groups, discontinuous groups of Möbius transformation of the upper half plane, which is, as I said, discontinuous in U, is called, any such group is called a Fuchsian group. Definition: G with these properties is a Fuchsian group. If S is a Riemann surface of a genus G without punctures, then its fundamental group has how many generators? Riemann surfaces are also abbreviated like this. So, what it is, the Riemann surface is a sphere. The Riemann surface of genus G is a sphere with G handles. Like this. A handle is a torus with a hole glued to the other handles, or in general to the Riemann sphere with G holes. This is the Riemann sphere. This is G holes. And we attach to every hole a handle, which is a torus with a hole. So G handles. And every handle has two generators of the fundamental group. The one like this, another like this. So the group P1 two G generators. On a torus, these two generators are like this. And it is well known that they commute. If you go along one generator, then along the other, then along the first generator in the opposite direction, then along the second generator in the opposite direction, then you will get a loop which is contractible. So there is, in case of G equal to 1, one relation on the generators. And in case of G, you have an analogous relation on the generators discovered also by Riemann, and so the group G also has 2G generators. Plus one relation. So, for a generator of a group G, it is a Möbius transformation that brings the real axis to itself, that is a Möbius transformation with real coefficients. Multiply the numerator and denominator by the same constant, and you will get the same transformation. Therefore, you have not 4, but 3 parameters, 3 real parameters. Hence, for this, you have 6G real parameters minus 3 because of a relation, and minus extra 3 because you can conjugate the group with the Möbius transformation, and you will get another group with, which uniformizes the same Riemann surface. So you have G minus 6 real parameters and the real dimension of this set is I did not write the for the set all Riemann surfaces of genus G is TG, take Müller space. So the real dimension of TG equals to 6G minus 6. And if you want to consider this real space as a realification of a complex one, then the corresponding complex space will be of dimension 3G minus 3. And formula that I will use in the next lecture. So the complex dimension of the Riemann surface with the genus G equals to 3G minus 3. a classical formula also known to Riemann. Now I switch to the simultaneous uniformization. The title of the is quasi-conformal maps as a uniformization. I will discuss now the quasi-complex structures. A quasi-complex structure is a forgotten complex structure. So you have a Riemann surface, and by definition, it is a two-dimensional manifold with the complex atlas of charts. So you have a covering of these manifolds by the atlas of charts. You have two maps to the unit disk, and the transition function is holomorphic. I will not recall you in more details what I have said before on this subject. So now suppose that you have this complex structure, this Riemann surface, but you forgot your complex structure. Is forgotten. And what is recalled is now you have these maps are, you have forgotten complex atlas, but you have a real atlas. Your transition functions are no more holomorphic, but they are only real diffeomorphisms. You have a real manifold now. And what is remembered is the following. Holomorphic functions are those whose differential is proportional to the differential of the complex coordinate. Classically, F is holomorphic if df is proportional to dz. And now we forgot this z. We only have one form written in real coordinates. Instead, we have, you can write still the real coordinate, the complex form. So we still write dz instead of dx plus I dy. But you have a form which is a this is dx plus I dy, and this is dx minus I dy. You have linear form, but if you multiply a vector by a complex number, the value of the form will not be multiplied by this complex number. This will be multiplied by this complex number, and this will be multiplied by the conjugate. So this form is proclaimed to be a holomorphic one form. And complex holomorphic functions F is, so this is the almost complex structure. This one form is proclaimed to be a holomorphic one form in the forgotten complex structure. So F is holomorphic, and this form is called quasi-complex structure. Quasi-complex structure. F is holomorphic in sense of this quasi-complex structure if and only if df is proportional to omega. Now we want to reconstruct the forgotten complex structure through the quasi-complex structure. For this, we need to find holomorphic functions that are holomorphic in sense of this quasi-complex structure. So the differential of f is f over z dz plus f over z bar times dz bar. The partial derivatives over z and z bar are defined in the same way as over x and y, and I will not recall how it is done. Any complex valued linear form in the real plane with the coordinate z may be written in this way. And the differential of f, these factors are called the partial derivatives in z and z bar. So I want that this will be dz bar. In order that this should be really the forgotten complex structure, one should require that modulo A is greater than magnitude of A is greater than magnitude of B. I do not explain this in details, just remember that this is the requirement. And we then get a so-called Beltrami equation. The ratio of these two partial derivatives is the same as of B and A. C is vanishing. So this function is denoted by mu. Mu is called the Beltrami coefficient. And the whole thing, with this part deleted, is called the Beltrami equation. So, we want to consider the whole Beltrami equation in the sphere. So this will be not the Riemann surface of genus G, but rather the Riemann sphere. There is no one atlas Z on the Riemann sphere. So passing to different charts, we will have a so Beltrami differential. Probably I will not enter the details because of the lack of time. Just I will speak about the Beltrami equation in one chart. The Beltrami equation in C with and in fact, considering Beltrami equation in C will give you the solution of the Beltrami equation in the Riemann sphere if you suppose that at the point infinity, the solution takes the value infinity. Alfors and Bers proved a theorem that was sort of a breakthrough in the theory of Riemann surfaces. Theorem of Alfors and Bers is the following. This is equation 1. Suppose that mu is continuous in C. Let me is continuous on C. No, this is too weak. Let mu be in L infinity of C. So it is measurable function, and with the bounded supremum, and the magnitude of mu is smaller than q, smaller than 1. The global solution exists if mu depends analytically or holomorphically on a parameter B, then the solution is holomorphic in the same parameter. So, this is the Alfors-Burrs theorem. It says that not only the almost complex structure is integrable, that is a forgotten complex structure on C, but if the corresponding Beltrami coefficient depends holomorphically on a parameter, then the solution depends holomorphically on the parameter. And this solution is the global holomorphic atlas on C. So let us now pass formal deformation of a Fuchsian group. So this F, the solution of the Beltrami equation, is called a quasi-conformal map. It satisfies this equation with the modulus of mu smaller than 1. And even separated from 1. Now, quasi-conformal deformations of a group G. First of all, I will give you a remarkable property of solutions of the Beltrami equation. Say F and H. So both F and H satisfy to the Beltrami equation. So dF and dH are proportional to the form omega that may be written in the following way. Mu is the ratio and A. So we called at the very beginning, divide the form mu by A, the form omega by A. We will get 1 here and mu here. And this will be the same quasi-complex structure. So they are both proportional to the form dz plus mu dz bar. So they are proportional to each other. Well, if H determines a local coordinate, and our solution, I did not say, this is a homeomorphism F of C to C is a homeomorphism. So if f is if df, differential of f, is proportional to differential of h, and h gives a local coordinate, then f is holomorphic in h. So now let us discuss quasi-conformal deformations of a group G. We have a Riemann surface S, and G is a covering group of S. If we factorize the upper half plane by the action of group G, this is the same as to identify all the covering surface that lie over one same point here. A universal cover and identify all the points that come from the curves with one and the same endpoint. This curve, and many, many other. So then we project the universal cover to here. This is P0. And when we identify the images under G, we take the map pi, which is first we map U to the universal cover, then we project the universal cover to S. So this is the map of U to S, and this map is exactly the identification of all the points of the orbit of the group G. So we can write that the factor space of U over G is S. And the question is, what is the factor space of the lower half plane over the group G? It appears that it is a Riemann surface which is symmetric to S. That is, you take a Riemann surface S, you take its atlas of charts, and you conjugate all the maps, all the coordinate maps, replace them by complex conjugate. And you get a new atlas of charts, and it is easy to see that the transition functions are still holomorphic. And this is the Riemann surface symmetric to S. So it is like this. The real line R is called the discontinuity region of G. This is the set where G, orbits of G, contains of no isolated points. And omega is the union of two half planes. And the factor space of omega over G is S plus S bar. So now we will solve the following problem. I will say it in words. You have another Riemann surface instead of S bar. And you want to find another group of Möbius transformations, not necessary Fuchsian, that is not necessary preserving the upper and lower half planes, but they should be discontinuous. They should be discontinuous, yes. The set of their limit points will be not a real line, but a homeomorphic image of a circle. And the complement to this topological circle is called omega, the discontinuity region. And the factor space of this omega over the action of the new group G will be one given Riemann surface S and another homeomorphic Riemann surface S1. So this is what I am explaining now. This will be quasi-conformal deformation. Take S prime homeomorphic to S let omega let K S to S prime be a diffeomorphism. Then there is a set of holomorphic one forms of S1 in the neighborhood of any point. You bring this set, you take a pullback of this complex structure on S1 and let omega be of a complex structure This is a pullback of the complex structure on S1 considered on S. So you have S equals U over G, and you have a Beltrami coefficient In fact, even I should write Beltrami differential instead of coefficient. The corresponding Beltrami differential is invariant under G. It is mu dz bar over dz, and we extend mu from U to C, letting it be 0 in the lower half plane. And we solve the equation df f z bar, the Beltrami equation, equal to mu on the whole sphere, on the whole of C. Then, not only f, but f of g are solutions of this equation. Say 2. Then, as I explained, f of g is a holomorphic function of f, but it is a holomorphic function on the whole Riemann sphere we added to f of infinity equals infinity. F of g is g1 of f. So this was for every g in the group G large. Therefore, the map F conjugates with the whole group G with the other group G1. And the real line under F comes to a topological circle, homeomorphic image of the circle lambda. Omega is the Riemann sphere minus lambda, and the factor space of omega over the group G1 is the following. In the upper half plane, we had, in fact, the complex structure brought from S1. So the factor space of the image of the upper half plane under G1 will be S1. And in the lower half space, F has zero relation. So F is holomorphic. So F is keeping the same structure as before. So here will be the Riemann surface symmetric to S. So this is a so-called quasi-conformal deformation of the group G, and formal deformation is the source of Beers-Griffiths simultaneous uniformization of a family of algebraic curves. Laura, I will borrow extra 5 minutes, okay? So, a simultaneous uniformization theorem. I will be very schematic. You have a polynomial P in 2 variables, and it maps C squared to C. You take a disk which contains no values. Its inverse image is a domain in C squared, and this domain is split into the algebraic curves exactly as I drew at the beginning of the lecture. You can fix one Riemann surface and map it onto the nearby ones along the complex transversal lines. You will bring the complex structure from the nearby leaves to the fixed one. And you will get if you have a cross-section here and the parameter B on this cross-section, you will get a family of Beltrami coefficients holomorphic in B. So, have a family of groups GB, depending on B holomorphically, with the discontinuity region delta 0B and delta 1B, and the union of these two maps of two groups is the union of these two domains is omega, and the factor space of omega along GB will be, if you take a point B here, then you get an inverse image, which is a Riemann surface called SB. And this will be SB. And the map of the universal cover, so no, this is not SB, but this is SB plus S0 bar. And delta 0B over GB is exactly SB. And the map of the universal cover over SB to the domain delta 0B is holomorphic in B, and universal cover of SB, it is HB to delta B0, is holomorphic in B, and therefore you get the simultaneous uniformization of the Riemann surfaces SB to the topological disk holomorphically depending on B. So I will say only that the groups with this property, their discontinuity region is two topological circles, their limit set is a topological circle. GB is called a quasi-Fuchsian group. And in the theory of Kleinian groups, there are more complicated groups, and I will speak of them in the next lecture. The next lecture will be closely related to this one, but still I will recall everything necessary, so it will be understandable from the very beginning. After the next lecture will be the last lecture in the complex part of my course, and the last three lectures will be about real bifurcations. They will be completely independent of all the previous 7 lectures, and this is the survey followed. Thank you.
Well, is there any question?
Thank you, Professor. I was wondering if first, why is it called a tech transformation there?
It is for the transformation of the universal cover corresponding to the element of the fundamental group. Covering transformation, but in English, deck transformation.
Is it a name, deck, or
Yes. No.
like a proper name?
This is
or?
just an adjective.
Okay. And then I was also wondering if when you take all the curves that are equivalent to gamma and their equivalence classes mapped into the upper half plane, is it like if you were to measure the relief of the surface without the holes, without the punctures?
Well,
the map
for
H?
simplicity, I considered no punctures, and you will add to the generators of the fundamental group the loops that circuit that a puncture, and these maps will be transformations that I will parabolic Möbius transformation. These are Möbius transformations with only one multiple fixed point on the whole Riemann sphere.
Okay. Okay, thank you.
Any other question?
When you were defining the Beltramic equation, is C a constant value or is it a function, so df is proportional to it?
Repeat, please, your question. I did not hear
Yes.
it.
When you, in the middle blackboard, you have df equals C times that one form.
Yes?
C, is that a function or is it a constant value?
It's a function.
It's a function, okay.
As the complex derivative. When in the classical complex analysis, your function is holomorphic, then its differential is proportional to dz, and the coefficient is the derivative. It is a function.
Okay, thank you.
More questions? Also for the people who are online.
So my question was, in the end, the family of Beltrami coefficients that are these the uniformization? Is that what you refer to as the uniformization? What we have at the end?
Let me see. You have the factor space. You have first one group GB. Its discontinuity region is a complement to a topological circle. When you factorize one topological disk over this group, you get one and the same Riemann surface as 0 bar. When we factorize another disk, topological disk, over this group, you get the Riemann surface SB that is desired. And you have first the conformal map of the universal cover over SB to this disk just because of this factorization. This is, in a sense, the same as to say that this disk is the universal cover over SB. And this group GB depends holomorphically on B, and this implies that the map of universal covers is also holomorphic in B.
Thank you.
Any other question? Also, people in Zoom? Well, I have one question also. Why in this last case we have that the limit points, they lie in this topological circle?
Because in the case of the Fuchsian group, the limit set the real line that is a circle on the Riemann sphere. And the map F is a global homeomorphism. So it brings a real line to a curve which is homeomorphic to a circle and is a quasi-circle by definition.
Okay. And why these Beltrami's coefficients, do they depend holomorphically in B?
I just said very, very briefly about this. You can take the normal cross-section as pieces of complex line with the complex coordinate on it and project the nearby fibers to the fixed one. And thus give a pullback of the complex structure on the pink on the violet fibers to the white one. And this map is not biholomorphic from one fiber to another, but as these transversal sections have their own complex structure, you may easily prove that the corresponding Beltrami differential will correspond holomorphically on the parameter of these transversal complex lines. I did not explain why.
Okay, thank you. More questions here? In Zoom? No? I think that's it. Well, let's thank Yulij again.
Thank you.